Here we're working with trig graphs in this little whirlwind tour of trigonometry. So here we're going to do these. Here are the angles from the unit circle, and we're just going to fill in the table. So sine of 0 is 0. Sine of pi over 6, that's up 30 degrees. That goes up to 1/2 on a 30, 60, 90 triangle. Pi over 4 is going to be square root of 2 over 2. Pi over 3 is square root of 3 over 2. Pi over 2 is clear straight up. That's a sine. The sine value is 1. At 2 pi over 3, we're back down at square root of 3 over 2. At 3 pi over 4, we're down at square root of 2 over 2. And then by the time we go down to pi, we're at 0. So what we've just done is gone through the angles like this. We've gone up 30 degrees, 45 degrees, 60 degrees, 90 degrees, and so the sine value has gotten bigger and bigger till we hit 1, then it got smaller and smaller, and pretty soon we're back down at 0. So now we're at 7 pi over 6, which is down here, so we're down at negative 1/2 for the sine value there. Then we'll be down at negative square root of 2 over 2, and then negative square root of 3 over 2. And so that puts us down here, and then down at 3 pi over 2, we're all the way down at negative 1. 5 pi over 3, it's going to start coming back up, negative square root of 3 over 2. And 7 pi over 4, it's negative square root of 2 over 2. And then that becomes, let me see, 11 pi over 6, we're down at negative 1/2. And then we're back to where we started at 0. So notice that this kind of looks like, if you start here, it goes up to 1. So if we were up to 1, and then we go back down to 0, and then we go down to negatives, and then we go back up to 0. And if we were to graph this like an x and y plot, instead of these guys going around this way as angles, if we were to graph it along, so all the angle measures are along here, it would end up going like this, and it makes a little wave. Let's look at that and see how another website has done that thing. This is kind of a cool little thing, and notice what happens as we go around here. This little thing says, see, it's right now we're in degrees, so if we're up at like 30 degrees, let's see, 30 degrees, there we are, right there. If we're at 30 degrees, the sine value is 1/2. So it's just measuring it, 0, 0, 30 degrees, we're up here. And notice that as we move around the circle on this angle, this green arrow says this is the sine value. So there's the sine value. And it'll go up to where pi over 2 hits 1, and then it comes back down. And so as we keep going, you see this arrow keeps going around here. That's how far we've moved along the right axis. So they're measuring the angle along a right axis and saying what the sine value is. And it goes all the way down to negative 1, then back up. And then if you keep going, you're just going around the circle again. Look at this. So you just go around the circle 2 or 3 or 4 or 5 or 10 times. That's pretty cool. So let's rewind back and see what happens if we put it in radians. Yeah, up here, this is pi over 2 radians, and you'll notice what that is. Yeah, pi divided by 2 is right there. The sine value is 1. And you go down here, that's pi radians. If I can get it right on there, 3.14159 radians, and the sine value is 0. So this has a 0 value at pi, and then at 2 pi, and then at 3 pi, and it just goes up and down and up and down. Let's look and see what cosine does. Oh no, we got to finish sine first. So if we were to go backwards, what would happen if we go backwards? So we go back to 0. Notice that it just keeps going. So we're negative 1/2, and then negative 1, and then up to 0, and then up to positive 1. And it just keeps following the same pattern no matter whether we go forward or backwards. So this right here, if this is 0, negative pi over 6 means we're down here, so we're at negative 1/2, and we get smaller. Negative square root of 2 over 2, negative square root of 3 over 2, negative 1. And then once we hit that point, we start coming right back up. So we're at negative square root of 3 over 2, negative square root of 2 over 2, negative 1/2, and then 0. So we're exactly opposite of these guys. So negative 7 pi over 6 is up here. That must be 1/2. Yeah, we're up in the second quadrant. So 1/2, and then square root of 2 over 2, square root of 3 over 2, 1, square root of 3 over 2. So we're going to be up here and then start coming down. Square root of 3 over 2, square root of 2 over 2, 1/2, and then 0. Now, what's interesting about this is notice that all of these things, if you stick in a negative number, you'll always get the opposite coming out. Even over here in the, no matter what you do, even when you got stuck in a positive to get a negative out, stick in the negative, it will be the opposite. Remember, that is actually what makes an odd function, is when you have f of negative x gives you negative f of x. So that's an odd function. Yeah, so the graph of sine starts sine of 0, 0, and it'll go up to 1, come down at pi, and then go back up at 2 pi. And then it will repeat like that over and over. Now let's look at cosine. Now the cosine of 0, remember now here, we're out on the x value. So the cosine starts at 1 and then starts going down. So it was at 1, now it's down at square root of 3 over 2. Then square root of 2 over 2. Then 1/2. And at pi over 2, where sine is up at its greatest, cosine is down as its smallest, and that's 0. Then we already start into the negative. So negative 1/2, negative square root of 2 over 2, negative square root of 3 over 2, and then negative 1. So cosine hits negative 1 back here. And so notice we start way up high, and then it goes through 0, and then it goes down here. And now it's going to come back up and end up right where we started, up high. Let's take a look at that graph and make sure that that's what we get. Yeah, so let's change and go to cosine here. And this is the blue arrow here. And notice that it's measuring the x value, but here we're still measuring it like an xy plot here. And so notice it starts up at the very top of its peak value, goes down to 0 right there at pi over 2. This is why we need to know the unit circle so well. And at pi it's negative 1, and then 0, and then back to 1. And it'll just keep going whether we go positive or negative. Now, something interesting about the positive and negative ones, notice this one, negative pi over 6, we're at square root of 3 over 2. Square root of 2 over 2, 1/2, 0. Negative 2 pi over 3 is at negative 1/2, negative square root of 2 over 2, and then negative 1. Notice that this guy and this guy have the exact same value, which kind of makes sense. If you go to an angle or down here, the x value is exactly the same. That is what makes an even function. When you have, you stick in a negative value and you get the same value back. The odd and even, if you recall, come from polynomials like f of x equals x cubed. If you stick in a negative value, a negative will pop out. Whereas this one, f of x equals, say, an even one like x squared. If you stick in 2 or negative 2, you'll get this exact same value. That's kind of cool there. Now, what does tangent do as a graph? Tangent, if we're going to write f of x equals tangent of x, well, that's the same thing as sine over cosine of x. Let's try and graph that guy right here. Now we know that sine, I'm going to graph him in red, starts at 0 and goes up and then down and then up and then down like that. And backwards, goes like that as well. And cosine starts up here and goes down, good, and then goes backwards like that. So let's do tangent, and notice what happens. Down here, if this ever equals 0, that means we are going to have a vertical asymptote. So every time the cosine equals 0, we have a vertical asymptote. Wow, there's going to be a lot of them because cosine hit 0. Now, what is, oh, right there, that's where the other guy was. Now, what is the tangent of 0? Well, the tangent of 0 is 0. So every time sine of x, the red, has a 0, we're at 0. And so we shoot up a vertical asymptote and down. So tangent of x is kind of weird. So what we need to see here is the domain and range of all of these. On sine, the domain is all real numbers. You can stick anything in. You can go at any angle and get something to come out, but you'll notice the range only goes from -1 to 1. That's important. Now on cosine, notice you can do the same thing. You can stick in any number. The domain is all real numbers, but the range is -1 to 1. Excellent. And then tangent, oh, this is a trickier one. The domain is, well, x cannot equal everywhere cosine had a 0, which was at pi over 2 and 3 pi over 2 and 5 pi over 2 and negative pi over 2. Holy cow. Dot, 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 dot. All of these patterns, any odd pi over 2 will give you cosine has a 0, and that's not in the domain. So domain does not equal all of those numbers. It can equal anything but that. But its range, notice what its range is. Its range, this shoots all the way up to infinity and down. So this actually has a range of all real numbers. Crazy that way. Sine of x equals 1/2. Well, where does that happen? How do you do this? Well, sine of x equals 1/2 actually has a lot of answers. If you think about it on a unit circle comes around like this, where sine is 1/2 is at this angle and that angle. So x could be a pi over a 6 or a 5 pi over a 6. You get two of them, but notice that you could take this guy and go around the circle once more. You could add 2 pi to it and get another answer, or do it again, or do it again, or do it again. So you can take anytime k is an integer and go around the circle that many times and land on this value and get an answer. Same thing with this one. And 5 pi over 6 plus 2 pi k. So you could go backwards around the circle as well, where k is an integer. So it's interesting that trigonometric equations like sine of x equals 1/2, they have billions and billions of answers. You can also see this on the graph. If sine of x is going like this, and you cross through it where y is 1/2, notice you get billions and billions of answers. All right, let's write another one like that so you can see what that kind of looks like. Sine of 3x equals, let's do square root of 3 over 2. Well, this means that 3x can equal, where's square root of 3 over 2? That means that you're right up here or right up there. So that would be pi over 3, and you can go around the circle a billion different times, or 2 pi over 3, and you can go around the circle a billion times. So let's make sure the k is an integer. That just makes sure we go around full circles. Good, but notice we haven't solved for x. Now if you divide everything by 3, that's right, we're going to divide by 3 and divide by 3 everywhere. So we can actually, our answers are pi over 9 plus 2 pi over 3k and 2 pi over 9 plus 2 pi over 3k. This is how you do it. You're going to solve equations like this by looking at where it's on the unit circle and giving all of the infinitely many solutions to it. Now this does cause a little bit of a problem. If you remember switching the x and the y places when we're trying to do inverses. Let's look at inverses here for a minute. On inverses, the x and the y switch places. So if this is sine of x, and it goes like this, up and down, then sine inverse, if you're ever going to try to do an inverse function and graph it, it's got to look like this. Oh boy. Is that a function? No way, vertical line test, which is exactly this, horizontal line test. If I were to say sine inverse of 1/2 and give one exact answer, it wouldn't pick these right here. So let's look back and see what inverses do with sine and cosine. So here's the graph that we had, and you'll notice domain and range would have to switch places. So if you had sine inverse, let's write it like this, sine inverse. Now be careful, this does not mean 1 over sine of 1/2 plug that into a calculator, and you're going to get pi over 6. We have to pick which one of those billions of different answers we're going to choose of all of these things. Of this right here, we've got to pick which one we're going to do. And so mathematicians had to decide. They're like, if it looks like this, we have to erase anything that is doubled. And so let's do it. Let's erase. We're going to erase from here all the way up so we never double. And this is kind of cheating. We just got rid of a billion different answers. Well, we did because we had to pick just one of them. Now, lest you think we're weird, we actually did this with square roots too. So we cut it down to, we chopped it down. So the domain for sine inverse, the domain is from -1 to 1. And the range, we chopped it down. What would give us 1? Pi over 2. So pi over 2, negative pi over 2. Yeah. So right there, notice that's the most convenient one, right around 0. So we've chopped them down. And cosine, we chopped down from, let me see, cosine inverse. We had to chop down. It looked like this. So its inverse would look like this, except that's not a graph of an inverse. So we chop all of, let me see, we want to have 0 here, the normal ones, and that would be the normal angles right there. Does that give us everything so we can chop off anything? Yep, that's it. So if we chopped off all the negative options, then we have as a domain, okay, reversing the x and the y, -1 to 1. And the range looks like we're from the angle 0 up to pi. Yeah, that's right. And tangent actually has this exact same thing. If we remember what tangents was, tangent looked like this, going up. And then it had a vertical asymptote and it did it again and again. So inverse tangent, if we switch that, goes like this, with an asymptote here and here. So on tangent inverse, the domain is all real numbers. We don't need an interval on that one. And then that's the domain. And the range is, negative pi over 2 to pi over 2. But they're asymptotes, so negative pi over 2 to pi over 2 with parentheses on it. Wow, those inverses are pretty crazy. There are a couple of things that you need to worry about.